that is correct. And sorry,
let's see. Oh yeah, he is.
Yeah, and so he will have this choose your own adventure. Let me add. Okay. Sorry for the quick thing here. All right. And yeah, I'll let him take it away. Sorry for the brief introduction, but he is at. Sorry, I'm fumbling. Oh no, where's my? Yeah, sorry. Yeah, he is at Technion University in Israel, and I'll let him take it away from here. Sorry. So I think this is. Oh.
Hi. Can you hear me?
Good morning.
Yeah, sorry. If you would like to speak, Omri, you're more than welcome to. This is.
No, it's okay. I mean, I just, I'm sorry that I couldn't make it physically. War is a bummer, and I'll do let you see the recording because the connection will be better, and I'm here for questions afterwards, and make good choices. And I'll see you in 7 or 15 minutes, however you choose.
Yeah. So we'll have a choose your adventure in the middle. We'll vote, and then we'll pick one of the options. Yeah.
Do you know how to click it?
Yeah, I do. Yeah. So do I?
Sorry. Good morning. I'm sorry I can't be physically here, but I'll try to make this brief and interesting and somewhat interactive. Closed loop behavior. If I see a visual stimulus like this coffee capsule, then I can have a motor output which will direct my hand towards it. But actually, this is not really an open loop because my action changed where my hand is, and that changed the visual stimulus I receive again. And more generally, in real life, usually the motor output I do affects the input I receive. This is very different from what happens in many laboratory settings where we have a reduced open loop scenario. For instance, if a monkey is looking at a random dot task, where dots are moving right and left, red and green, and then it has to saccade, the direction in which it saccades will not affect how the dots will move in the following trial. Likewise, when we have a model or an RNN, a recurrent neural network that receives inputs of motion, color, and context, and that goes through the recurrency, which is sort of a closed loop, but the output itself of the network does not affect the input it receives. There is reward, which is a point I will not touch upon now. One can think of an even more extreme example, that instead of me being physically here and looking at the audience and seeing whether you're still alive, asleep, what's going on with you, I'm a pre-recorded video that has no relation to what you're doing out there in the audience. Now, does it matter? Will you learn more or less when I'm in open loop or closed loop? And let's take a case at hand. Bicycles. To learn to ride a bicycle, you need to do 2 things. First, you need to balance yourself, go to the right or left, not fall down. And also you need to learn how to paddle. Now, one can do a curriculum learning of sorts. Either you can first learn to paddle and have somebody else take care of the balancing, or you can first learn to balance with a balance bike and later on learn how to paddle. Now, if we care about the dynamical control theory part of balancing yourself, then training wheels are a bit of an open loop setting where somebody else takes care of the balance for you. Whereas the balance bike is a closed loop scenario. Now, does it matter? Science to the rescue, it does. People actually checked it and kids learn faster with the balance bike. So instead of bicycles, you have here a talented graduate student in the lab ask the same question in RNN form. Given 2 RNNs, all else is equal except open versus closed loop. How do we do the balance bike? We take our RNN, it has an output. That output feeds into the environment, which has its own dynamics, and that gives rise to an observation Y that is fed back to the network. So the input to the network is the output of the environment, and the output of the network is the input to the environment. In contrast, the open loop setting is one where the network still receives the same input, gives the same output, but now it's imitating an expert, a teacher. So that teacher already knows how to ride a bicycle. It receives the input and it knows whether to correct to the right or to the left. And all we do is imitate this teacher. Now, does it matter? Okay, we're not going to have bicycles. We're going to have a double integrator. This is the classic control theory task. A unit mass is over here, but it really wants to be over there. So there's a controller, that's our RNN, that's going to help it. The controller sees the position of the unit mass. Crucially, it does not see velocity, which means it is partially observable. That is why we need an RNN, which has memory and can infer velocity. What the controller does is apply force or changes velocity of the mass. And we can also write this, read the subtitles. This is the, classic control theory version of this. Now, let's see how the learning dynamics look for open and closed loop networks. We are going to focus on the test loss as a function of learning epochs. First, the closed loop network. We see that it gradually learns. It has three distinct stages: fast, a plateau, and then fast again. Notice there's a logarithmic scale on the learning axis. And what will the open loop, the imitation learning, do? It also gets better, but then suddenly it gets really bad until it finally converges. Let's take a closer look at this. Now we're going to separate a train and test loss. Test on the left, train on the right. In the closed loop setting, we see they're very, very similar, which makes sense because it's the same distribution. In the open loop, however, we see that while learning in the train set in the open loop is monotonic, the closed loop test set has this weird behavior. Also note that when the test loss drops 4 orders of magnitude from here to here, at the same time, the train loss only drops roughly 1 order of magnitude. So it really is doing a different task. Now that we see they are different, the question is, will we go to open-closed difference or 3 stages? You'll be able to choose in a second, but before that, a bit of math background you'll need for both of them. We're going to work with linear RNNs because they allow us analytical insight. So the RNN is a classic linear network, recurrent connectivity, input, and the output is given by some readout vector. The state is also a linear dynamical system, which means that we can stack them together, both world state and RNN state, and then we have a linear system that has this block structure, both the environment dynamics, RNN dynamics, and the RNN world interaction. So this matrix is going to serve us when you choose where you want to go next. So what will it be? 3 stages or open-closed loop difference?
All right. We'll do a vote. So would you want to do the who's for open closed loop difference? Okay, well, that already took a majority. And who for 3 stages? Okay. So I think we'll do open closed.
Yeah.
All right.
Excellent choice. Why are open and closed loop so different? Well, remember the P matrix I told you about that has the environment dynamics, RNN dynamics, and their interaction. We want to make it a bit simpler. So we're going to restrict ourselves to a low rank connectivity matrix, UV transpose, rank 1, That in turn will cause our hidden dynamics of the RNN to be two-dimensional. They are spanned by the input and recurrent connectivity. And this allows the effective matrix to be a 4x4 matrix, and only 4 numbers, these overlaps, determine the entire dynamics of both world and network. Now, the intuition is the following. To solve the task, we need 2 things, really. One of them is a fast control policy to reach the goal quickly. So if the target is to the left, we want to push hard to the left. And that requires to grow the output weights, which correspond to the overlap input-output, ZM. On the other hand, we need to pull the brakes, right? So once we get close to the goal, we want to slow down. In order to know that, we need to infer policy, and that requires the internal representation or the eigenvalues of the RNN, and they are captured by UV, that overlap, the internal overlap. So let's look at how these 2 overlaps develop in open and closed loop settings. First, let's look at the open loop, the red one. So you see that the first thing that happens is that the input-output overlaps grow. Only later, the eigenvalue changes, the VU overlap. On the other hand, if we look at the closed loop learning, then we see first we build the internal representation, only then do we really change the input-output overlaps. So the open loop first does policy and only then internal representation, and the closed loop is the opposite. And the reason is that open loop learning does not see the consequences of its actions. It can just push as hard as it wants on the outputs because the teacher, the expert, the open loop supervisor will pull the brakes for it. So it doesn't have to worry about it. Whereas the closed loop feels the consequences of its actions and therefore puts more emphasis on the internal representation. Where to now?
Should we do the second option, the Y3 stages? Okay. Does that sound good with everyone, or?
Excellent choice. Why 3 stages? So we see that there's a rapid decrease, a plateau, and then a third stage where we really drop the loss. Okay, the first stage is really a P in a PID controller, or a negative position. This is sort of saying, look, if the goal is to your right, I better push you to the right and not to the left. And that's, quite a nice insight that will really drop the loss compared to pushing it to the opposite direction. Problem is, this is an unstable policy. So if you push it to the left, but it also has momentum, then it's just going to get too much to the left and then too much to the right, and it's just going to oscillate more and more, and it will be unstable. So while this is better than pushing it in the opposite way, it's still not a very good policy. Next, we need to build a world model. We need to know that it has velocity. When we do that, the eigenvalues of the P matrix I told you about before, now they become stable. And you see this zigzag pattern over here. The zigzag is really a balance between 2 forces. One of them, you really want to push it to the goal position. The other is that you are aware there is a long-term consequence of your actions because you're in closed loop. And that actually pushes you, the eigenvalue, in the opposite direction. And then this zigzag pattern is this balance of 2 forces, the short-term and long-term loss of your loss function. And the balance between them gives rise to the plateau. Once you're already stable, it's easier to fine-tune the model pull a couple more eigenvalues, and have a much more rapid arrival to the goal position. Where to now?
Yeah. Yeah.
Release the data. Yeah.
Yeah. We have a little bit more time. So.
Does this have anything to do with real data? So, Chen Avraham and Firas Mawase at the Technion train human subjects to track a moving target. When the subjects move their hand, the target moves as if reflected by a mirror. So this is quite a challenging thing. Moreover, the target moves using a sum of several sine waves, so it sort of moves around here and there. We train a network, an RNN, to do the same task, so the target moves with the sum of sine waves. And we see a very similar phenomenon. Open loop, it gets worse and then gets better. The closed loop has a plateau, but it actually has several plateaus, one corresponding to each frequency. And moreover, we can show that they learn the frequencies from the slow frequency to the fast frequency. And when we compare the rate of learning in our RNN and the data, we see a very similar trend. So in closed loop learning, the RNN learns slow followed by fast frequencies, very similar to what human subjects do. Where to now? Okay, so what did we have today? We saw that closed loop gives you a trade-off between short-term control and long-term stability. Life is closed loop, but many experiments and models are open loop, and this matters for learning trajectories. RNNs can be a model system to capture this closed loop behavior, and learning can uncover structural links and constraints between the parameter space and the effective overlap or behavior space. Thank you very much for your attention, and I'm here for questions.
And yeah, we have Omri here for questions, and so we will take questions from the audience. Yeah.
No, just make it here.
Hello, thanks for the talk, very nice. So actually I come from control theory and this from the background in control theory, and this is reminding me a little bit of adaptive control, where we are trying to do control and learn at the same time. So a huge topic in adaptive control is how to ensure the stability of the closed loop system while learning, while here it seems that you have this first phase where it's unstable. So I was wondering if there's some ways in which you could impose stability of the closed loop while you are learning.
Okay, so in this case, in a sense, because we have a trial structure, then every trial has a predefined time window. So although it's unstable, you sort of stop after 50 time steps or so, and so the control is not really online in the sense that there's one continuous time stream like you would have in a physical system, and therefore what the trick here sort of is that we reset the trial every time, and therefore we can give it another go. If you do want to enforce stability in something that is online, you have methods like forced learning is a famous example where there's a recursively square thing that ensures very fast plasticity. But in a sense, I guess the way to do that is either faster plasticity or some structural constraints that give you boundaries on the system.
Okay, thank you.
Hi. I think I might have missed something in the teacher setup. You said that when the in the open loop setting, the network can just push far and then the teacher will take care of the overshoot. sorry, I just heard my own voice. What's the closed loop control with voice is very hard. Or extra. What's the what's happening with the teacher loss? Is it controlling it and overriding the outputs, or I think I missed something about how that loss was set up?
Okay, so in a sense, you can think of it as, let's say that you're driving, that you're in a car, but somebody else is driving, and you have your hands on the steering wheel as well, and you're trying to match. So you see the road ahead of you, okay, and you see that you need to turn to the right, but there's another person that's actually turning the wheel to the right. And what you have to do is imitate that other person. So you see the visual stimulus, you see that the wheel is going to the right, and you move the wheel to the right. But if your command is to move the wheel too much to the right, then you're trying to do that, that's fine, but the next time step, control is actually by the teacher, the expert. So you'll not crash. Okay, so that's like the intuition. Formally, what happens is that you're provided by IID inputs, and both you and the teacher receive these inputs, and the teacher provides the output, and you try to imitate the teacher. So the teacher is somebody that can already solve the closed loop task, and this is known as imitation learning. By the way, this is similar to what language models do, right? You try to predict the next token in an open loop because you get a text that somebody else produced, and then in the closed loop you will try to do this online. So this imitation type learning is actually very common.
Thank you.
Yeah, so maybe following up a little bit on this, in more complex scenarios, I could imagine that due to the feedback, you could, since you're influencing your observations in the end, you could get less valuable observations because you're in the beginning not really knowing what you're doing, or the agent's not really knowing what it's doing. So it's kind of destroying the meaningful observations. Do you think there could be a way to have like the best of both worlds scenarios where you have like a teacher that sometimes corrects you to stay on track to get meaningful observations, but then in the end have partially closed loop systems again?
So in a sense, this is, teacher forcing. There's a question, this is something we did not address, of whether there's an optimal curriculum of teacher forcing where you can start by, having somebody else drive and then gradually let go. Because what you really want to do is, as you said, you want to be in the correct input distribution so that you sample relevant parts of your input space. And if the closed loop, let's take the first question. If it's unstable and nobody stops you, you're going to go to infinity and that's it. So the teacher can put you in the relevant space, and then you have to let go to sample the closed loop, because eventually the input statistics you really care about are the ones of the stabilities and instabilities of the closed loop setting.
Thank you. Let's thank our speaker.